Good morning. In this video, we are going to discuss about the geological factors which affect tunneling, or what are the considerations, what are the geological investigations for tunneling, what are the considerations, and what are the methods to be adopted, or what are the important points to be considered when tunneling is done in when the particular rock layers through which the tunnel alignment is there, or tunnel is aligned. Okay, so that contains secondary structures like folds, fault. Then when the groundwater conditions vary, when the groundwater is above the top of the tunnel, what are the how tunneling has to be conducted. So all those factors which affect, geological factors which are to be considered while tunneling. So that is what we are going to discuss in this video, and also we will be discussing about the Toposheets and how Toposheets, what are the important terms in the sheet, and what is the purpose and how structural mapping is done. And we will also discuss about two different types of compass, that is Clinometer compass and Brunton compass, which we use for geological investigations. Okay, so we'll start with the tunnels. So we know tunnels are underground routes or passages which are driven through the ground, normally without disturbing the overlying soil or the overlying rocks. Depending on the purpose, tunnels are classified into traffic tunnels, hydro power tunnels, and also for public transportation, that is public utility tunnels. Public utility. Okay. Highly mountainous terrains are where we have to do tunneling, because so that is the terrain which necessitates the construction of tunnels. So normally you have to go around a mountain, so the length will be very high. So in that case you have to construct a tunnel. You have to drill through the inside of the mountain, and that is the shortest way, where shortest path normally observed. So geologically, when we are addressing this tunneling, we have tunneling which is normally done through rocks, and also soft ground tunneling. So when it is necessary to construct a tunnel, or some areas, some soft ground, if it is encountered in between the path of a tunnel, there a soft ground tunneling is also required. So what are the objectives of these geological investigations or tunneling? First, we have to select the tunnel route alignment. So when you are selecting the alignment means the center, the direction of the center line of the tunnel. So that has to be that should be selected in such a way that unsafe conditions created due to the secondary structures, or due to groundwater conditions, etc., should be avoided as far as possible. And when you select the excavation method also, it should not disturb the overlying rocks or overlying soil. Also, the design of the tunnel should be done in such a way that it causes, it is cost effective, and it provides great stability, and also it will not cause much of environmental hazards, and it does not disturb the ecological balance of the area through which the tunnel is to be done. Then we do a lot of surveys before constructing the tunnels. Preliminary surveys like the geological, geophysical, geochemical methods, aerial photography, seismic surveys. Then in order to know the topography of the area, lithology, hydrological conditions, then occurrence of different secondary structures, reserve rocks, etc. And we will also predict a certain, or will propose alternate tunnel routes. So all these are done in the preliminary survey. Detailed survey means we collect samples by drilling boreholes, exploratory shafts and pilot tunnels. So boreholes are constructed, then exploratory shafts are vertical shafts which are constructed to know about the different layers of rocks and their strength aspects, and also pilot tunnel construction is also done. And we collect rock samples, and these samples are tested in laboratory, their mineralogical composition, their compressive strength values, then modulus of elasticity, porosity, permeability, and their chemical resistance to weathering and their chemical characteristics. All these are determined. And these surveys we conduct, and that is how we get a geological profile of the area. So here you can see this is one particular photograph or a figure which shows here you can see this B shows a vertical tunnel. So these are pilot shafts, or these are actually the exploratory shafts or boreholes which are constructed to take to collect samples. Okay. Also you can see here the different secondary features like the folding, then faulting, etc. can be seen. And here you can see a fold is there on the right hand, on the right side you can see there is a folding what an anticlinal fold is there. And also you can see at different temperature that the change in temperature as we go down, and also the elevations are also shown on the right. So based on all this we propose the tunnel alignment, and also certain extra alternative tunnel routes are also proposed. Okay, so considering so after doing the preliminary survey and detailed survey, after collecting the samples and testing them in lab, we will get to know about the geological profile. So this is a sample geological profile, and based on this we propose the alignment. So when all these geological information which are gathered from the preliminary and detailed surveys plotted along a longitudinal section with the axis of the tunnel as the section line, we get this figure, and this is called as the geological profile. So geological profile is actually a diagram which is plotted with the information gathered from preliminary survey and detailed survey. Okay. Now what is the general nature of this particular geological profile? It has a longitudinal section. It is all these data is plotted with the axis of the tunnel is taken as this. That is, axis means the central longitudinal axis of the tunnel, the central line of the tunnel. So that line, that particular, if you cut the tunnel, okay, in such a way that the longitudinal section is seen, okay, that is how we draw the geological profile. So this photograph which you see is the geological profile, and it is the most important geological record which is available, and this is the guideline for tunneling. It provides information about the location, then about the depth of borehole, type of rock, then structures, as I told you, the secondary structures like fault, etc., and also the groundwater conditions, okay, hydrological conditions, and also the ground temperature. So important, if you are asked to write about explain geological profile, what you have to write first, what is the definition? Okay, so for geological profile we need to do preliminary survey and detailed survey and collect all the data. Then it is plotted, the data obtained is plotted along a longitudinal section with the axis of the tunnel is the section line. So the diagram you got, the profile you obtained, that is called as geological profile. And this profile is actually it provides information about the location of the tunnel, then the depth of the location of boreholes, where the boreholes are located, what is the depth of borehole, what is the type of rock found in different strata, structure of the rock, hydrological conditions, ground temperature, etc. So if we have consolidated rock means hard crystalline rocks, then throughout the alignment of the rock, then it is favorable. So another important factor is that these hard rocks, they have to be excavated. So in order to excavate these hard rocks, you may require rock blasting methods, or you have to use tunnel boring machine. Tunnel boring machine we have seen in our previous classes, so you may refer back. Then igneous rocks like granite, diorite, syenite and gabbro and basalt. So all these are very hard and consolidated and crystalline rocks. So these are also favorable for tunneling. Similarly, sedimentary rocks like sandstone, limestone, dolomite, quartzite and metamorphic rocks, marble, gneiss, quartzite, phyllite and slate. So these are the different types of consolidated rocks. So consolidated means they are hard and crystalline, they are favorable for tunneling, and if you find any of these rocks, okay, like granite, diorite, syenite, gabbro, basalt, sandstone, limestone, dolomite, quartzite, marble, gneiss, quartzite, phyllite, slate, etc., then that is actually those rocks are ideal, or they are they are favorable conditions for the construction of tunneling. There won't be much risk or unsafe conditions arising if these are the rocks. Whereas if soft rock is found, soft rock like shale, which is friable, that is easy to break, and it is poorly compacted sandstone, chalk, then porous varieties of limestone, dolomite. That means limestone, dolomite, if they are without any pores, okay, they are very hard and compact, then they are consolidated rocks. But if it is porous, then that is why we have stressed that in the detailed survey we have to check the porosity, permeability, modulus of elasticity of the rocks. Okay, so those values, even if it is limestone, if it is porous, then then also we can do tunneling, but there are there can be a risk or caving in, or there can be water leakage in the inside of the tunnel. So if it is meant for a particular purpose, then due to the leakage from above, certain sections of the tunnel may be unsafe, or it won't serve the purpose for which it was designed. Okay. So slate and phyllite with high degree of cleavage. So slate and phyllite without cleavage, we can consider it as an ideal condition, whereas if slate and phyllite with high degree of cleavage or decomposed varieties of igneous rock which shows which has undergone weathering and decomposition. So all these are categorized as soft rocks. The cost of excavation is low, because it is easy to bore or drill through these rocks because they are soft rocks. But since these rocks are not self-supporting, permanent and temporary lining is required. So this lining adds the cost. So consolidated rocks means we have to use tunnel boring machine. So it is very hard to drill through the strata, but it is stable and it offers very hard and crystalline structure. So it is highly durable, and it will be safe. Whereas soft rocks means the excavation cost is low, still we can do tunneling through these rocks, but we can easily drill the rocks, but they are not self-supporting. So it will lead to you have to provide lining, and all concrete lining is to be provided. So that actually increases the cost. So when you are stressing about the rock types, we can see that igneous rocks, they are competent, but they can, it is difficult to drill. Okay, you may require large machinery, etc., but lining is not required. So that cost of lining you can save, whereas the drilling will be costly. Whereas sedimentary rock, they are soft, so easy to drill, but the cost of lining is there. Metamorphic also similar to granite iron. Okay. Now we are going to study about how the geological structures affect the selection of affects tunneling. Okay. So here you can see first figure itself, A and B are there. So when you are tunneling in a horizontal layer, tunneling through horizontal layer, in the figure A, tunneling in horizontal layer, figure A, that is a safe condition. Here the beds are parallel and the shape of the tunnel or the cross section of the tunnel is a D-shaped tunnel. The roof of the tunnel is horizontal. Okay. Whereas in the if you are having horizontally bedded or horizontal layers, bedding planes, in that area you shouldn't provide a horseshoe shaped or a tunnel with a top in the shape of an arch. Okay, so that is unsafe. So if the bedding layers are horizontal, the ideal shape of the roof of the tunnel is horizontal. Okay. Whereas in the second figure, we are considering two cases. The first figure, that is A, is the tunnel center line or the tunnel alignment is parallel to the tip of the layers. Okay, so here you can see D shows the direction of the dip of the layers. So the tunnel center line of the tunnel is also parallel to the dip of the tunnel. Okay. Whereas in the B figure, the tunneling is done parallel to the strike of the layers. And if it is like steeply inclined, here in the first figure, tunneling in steeply inclined and inclined strata parallel to the dip. So parallel to the dip direction, if it is tunneling is done in a steeply inclined way, and if it is like tunneling in steeply inclined, if it is parallel to the strike, then it is unsafe. Okay, so if it is parallel to the dip, it is safe, and if it is parallel to the strike, it is unsafe. Okay. And regarding tunneling in areas where fold is present, you can see that if the tunneling is along or through anticlinal folds, then the high pressure occurs on the outside and low pressure zones are in the inside. So low pressure in the middle region, and in synclinal, high pressure occurs in the middle region. Okay. And if it is faulted region, you can see that tunnel in a faulted region, a fault inclined to the tunnel forms highly unsafe location, because as you can see in the figure, if there is a fault plane, there are chances that the tunnel this area, that is the top of the area, may undergo slight displacement, and it will lead to the collapse of the tunnel. Also, the hydrological conditions, how it affects tunneling. Okay, here is a photograph which shows the that is tunnels above A tunnel. So here you can see the letter A, and if the tunnel is aligned, okay, as shown in A, the tunnel is lying in impermeable strata, because here the water table is well below the tunnel. So that is actually most preferred. So the tunnel will not have any disturbance due to change in the groundwater table. Okay, it is well above the A. It is the tunnel A. If that is the alignment, then it is well above the water table, and it is the most preferred, and it will not have any disadvantages, or the unsafe conditions will not arise due to fluctuations in water table. Whereas if you are selecting the tunnel alignment as shown in B. B means what? The tunnel is partly above and partly below the water table. So here lining and proper drainage needs to be provided, and then only it becomes safe. Whereas if a tunnel is completely lying below the water table as seen in C, it is not at all preferred, because such tunnels will have that will be highly unsafe. Now another condition which may arise, which may affect the stability of tunnels, is the overbreak, that is tunneling through hard rocks require removal of some rocks outside the proposed perimeter. That means when you are drilling in a hard strata, what happens is this, you may have to remove some extra rock. That means you can't exactly drill like along the when you are drilling, some amount of rock from outside the periphery of the tunnel will also get removed, because you are blasting. Okay, so after this excess quantity of rock which is removed, that we call as overbreak. So after removing this, again you have to construct the lining, etc., and you have to construct the tunnel as per the design shape. So the geological factors which govern the amount of overbreak are the nature of rocks, the orientation of joints, and orientation of the bedding planes. So if the overbreak is excess, you may have to again the cost will be more. You have to fill in with concrete, and you have to arrive at the required shape. Okay. So if the overbreak is less, then that type of rocks are ideal for the construction of tunnels. So the nature of rocks, orientation of joints, and bedding planes, also all these affects the amount of overbreak, that is the excess amount of rock that is removed. So with that we have discussed so many geological factors which affect tunneling. So we have the important points are: first we need to have a geological profile. Then if consolidated rocks are present, what are the conditions, what are the factors? If it is soft rock, what are the criteria? Okay. Then if it is the layers are horizontal, the top or the roof should be flat. Okay, that is the safe condition. Then if the tip if it is steeply inclined, then the tunneling should be done in steeply inclined. It should be parallel to strike. So parallel to strike is the ideal condition. And also in anticlinal folds, you can see that the low pressure will be in the middle region, whereas in synclinal, high pressure will be in the middle region. So low pressure means it is easy to drill through the inside layers. Then fault regions should be avoided, and also groundwater conditions. We prefer the tunnel should be well above the water table, or it is like partly above and partly below. That both those are preferred, but partly above, partly below case we have to provide lining and also drainage. Whereas if the tunnel is below water table, that is not preferred. And also overbreak, the amount of overbreak should also be, amount of overbreak is also governed by geological factors like the nature of rocks, orientation of the bedding plane. Okay. The next topic which we are going to study is topo sheets. So what you see here is a sample topo sheet. Topo sheets means it is topographic sheets. A topo sheet contains information about an area like major locations, the road networks, railway networks, settlements, canals, rivers, electric poles, etc. It is characterized by large-scale detail and quantitative representation of the relief features, that is the natural features, and that is the hills, mountains, valleys, etc. And that is usually using contour lines. And this another important peculiarity of topo sheet is that it contains details about the natural features and also about the man-made features. So topo sheets, what are the uses of topo sheets? So normally we use topo sheets for geographic planning or large-scale architecture, earth science and other geographic disciplines, mining, and also for various purposes like in order to know about the different surface and subsurface features of the earth, and also for recreational purposes, etc. We use this topo sheets. Topographical maps are prepared using photogrammetric interpretation of the aerial photography. Then also we use remote sensing techniques for preparation of these topo sheets. Older topographic maps were prepared using traditional surveying instruments. So this we have learnt about this in GIS also. In surveying in GIS also we have learnt about this. So here you can see this is a topo sheet of Himachal Pradesh, and you can see that the sheet number, index, etc. will be marked on the top right corner, and the district and the which state, which district, then the latitude, longitude, etc. are marked, and also you can see legend, that is the symbols, then map, scale, distinct outline, etc. all those are shown in this. So here you can see this representative fraction. As you know, it is a ratio of distance between the the distance on length on map by actual ground distance. And what is scale, then contour, it is a line connecting points of equal elevation above the sea level. Then contour interval, then contour lines are sometimes thickened at regular intervals to make it easier to read. So certain portions will be thick. One contour line will be there, and in order to easily distinguish and easily identify, certain portions of the contour lines will be made thick. So that we call as index contour. Then the height also will be calculated using trigonometry. Then benchmark will be shown. Then if it is mixed forest with more than 2 varieties of trees growing in a close proximity to it, it will be marked as mixed forest. Then open jungle, then embankments or raised soil or raised areas. Form lines, the form lines are contour lines, but they show only approximate height above sea level, and they are just used to indicate the elevation of the area, which are not accessible for proper survey. Okay. So Government of India has adopted metric system for all the measurements, and all the maps issued by Survey of India were drawn to a scale of 1 in 50,000, 1:50,000. In the system, the survey territory is divided into 100 km by 100 km square, and each square is denoted by English alphabet. So this system of mapping is called as National Grid Reference. So here you can see the grids, which are called as the national the system of mapping. Here you can see the different grids. Okay, and this we call as National Grid Reference. And also in the next figure you can see the legend. Legend means the different terms, important terms. So in order to identify and characterize these areas, we do structural mapping. So structures, secondary structures like fault, fold, etc. Fold itself, we have synclines, anticlines, okay, and there can be lineaments. So understanding these secondary structures is a very important thing when we are going to interpret the crustal movements, okay, which are responsible for the present terrain. So the structures can indicate potential locations of oil and gas reserves, and also we are able to characterize both the underlying subsurface geometry of rock units and the amount of crustal deformation and the stress which is experienced at a certain location. So detailed examination of these secondary structures can be obtained by conducting seismic survey. Structures are also examined for getting important clue, where crustal movements are taking place, and where there are high risk areas where earthquakes or landslides or volcanic activity may occur. So the identification of fault lines can also facilitate the land use planning by limiting the construction over potentially dangerous zones of seismic activity. So we have to identify such areas which are which may be which are potential zones of earthquakes and other hazards, and in those areas we have to the land use should be controlled. So again, this is another photograph which shows, you can see that in a 2D plane we have you can see the different types of rocks are also marked. They are shown in different colors, and for example the different years of formation, that is based on the classification of rocks based on their origin. They are all classified and shown in different colors, and also you can see the velocity, that means like how the crustal plates are moving, their direction and their velocity in millimeter per year. So here you can see a blue arrow. Okay, you can see some two big arrows, blue color arrows. Okay, in one arrow it is marked 26. Okay, on the top of the arrow it is marked 26, and here it is marked 20. Okay, so blue arrow with on top 26 and 20, that is marked. So these two blue arrows actually they represent the relative velocity in millimeter per year of the lithospheric plates, and these thick blue lines shown here, thick blue lines, you can see one on the right side, like there is a Red Sea, so Red Sea, and on the center you can see a thick blue line. Okay, so that thick blue line, that actually there are two arrows also. So these arrows represent the, so that thick blue line represents the axis of the oceanic accretion, and it is like the rate of spread that is also marked there. Then the red lines, red thin lines, they show the fault lines. See here you can see fault lines, and subduction zones are also shown with thick red lines. They show the subduction zones. Okay, and there is also this arrow as subduction. That means one layer may go down below the other. And the strike slip direction, that is shown using the blue line with the half arrow. So this is a strike slip. So we have learnt about strike slip in fault. Okay, so all these are well represented in a map. So this we call as structural map. So that means it is actually a topo sheet, but it has the crustal, like the secondary structures, and their the movement and the velocity of the lithospheric plates. All this is shown in the map. So this type of maps actually helps us to identify potential hazard zones like earthquake zones, landslide zones, volcanic zones, etc. And also it will help us to reduce the casualties due to such natural hazards. So we can identify such zones, and we can plan the we can land use where constructions are to be limited, where which areas where minimum pressure to be given to the land. So all those construction activities can be limited in such potentially dangerous zones of seismic activity. So this is the use of this particular structural map and also topo sheets. Now, how in order to prepare this particular structural maps, we need two important instruments, that is Brunton compass and um, Clinometer compass. Okay. So, what you see here is a Clinometer compass. It is an important instrument which is used by geologists and engineers who are working in the field of earth science or geological survey for mapping and also for navigational use. It actually, you get orientation from this particular compass. We get the dip of the rock, height of the geological and geographical features, angles, and you get even it can be used in harsh field areas. So it is usually fixed to a rectangular plate, which is that rectangular plate is made of cast iron or it may be a plastic, in such a way that the 180 degree diameter, that is the north-south direction, is parallel to the length of the longer side of the rectangular plate. The division on the circle from 0 to 360 degree goes anti-clockwise. So it is marked anti-clockwise, and the east and west are thus opposite from the normal compass. So this is this particular compass is marked in this way so that it is you can calculate the azimuth of the strike directly from the position of the north. A clinometer is normally situated to the compass needle with the half circle that is divided from 0 to 90 degree on either side. The angle of dip is measured by its position on the half circle. Next type of compass is Brunton compass. So Brunton compass is it is different from Clinometer compass. It was actually designed by a Canadian geologist, D.W. Brunton, and it was built by William Ainsworth. It is a type of specialized instrument. It is used for field mapping of geological objects. The dip angle, strike, fold, hinge line, axial trace, axial plane, etc. can be measured using Brunton compass. A variety of the planar and linear structural, sedimentary and stratigraphic geological features, all these can be measured using the Brunton compass. It has three main parts. First, what you see is a box. Okay, there is a sighting arm and a lid is there. It contains a needle. Then there is a small level, bullseye level. Like you in your total station and all, you can see a bullseye level in order to check whether the tripod is horizontal. So similarly, you can see a bullseye level in the Brunton compass also. Then there is a clinometer level and a clinometer scale is there. Then there is a damping mechanism. This damping mechanism is used to efficiently stabilize the needle, and there is a lift pin, and this lift pin is used to lock the needle. Side brass screw is there, and there is an index pin to set and display the declination. The graduated circle is used to read the bearing, and also the needle has two ends. There is a north-seeking end and a south-seeking end. Most frequent use of Brunton compass is carried out in the field in order to measure the strike and dip of the geological feature. So this is actual photograph of a Brunton compass. So it's very compact. It's a pocket instrument, and it's used in preliminary topographic and geological surveys. So the basic difference between clinometer and Brunton is that clinometer is an instrument for measuring angles of slope, elevation or depression, and also there is a tilt indicator. You can measure the gradient or the slope, and they measure both positive slope and also negative slopes. And these clinometer has three different units of measurement, that is degree, percentage, and also topo. Then Brunton compass, it is Brunton pocket transit. It is highly precise, okay, and this is used by land surveyors, engineers, archaeologists, etc. for navigation and also to measure the strike and dip of the rock layers in field. It is a specialized instrument used widely by those who need to make accurate navigational and slope angle measurements in the field. This is like primarily geologists, archaeologists, environmental engineers, mining engineers, they use the Brunton compass. So this is actually a pocket type transit compass. It is highly accurate and mainly used to measure the dip and strike of the rock layers. And clinometer means you get the elevation, declination or depression. Okay, elevation, that is the vertical height. Then the slope, whether it is positive slope, that is as seen, that is upward slope or decline. Okay, and so clinometer, basically if you are asked, if this difference between clinometer and Brunton compass is asked as a part A question for 3 marks, you just need to write the basic differences. Clinometer for measuring angles of slope, elevation or depression with respect to gravity. It has a tilt indicator. You get the gradient, that is the positive slope or negative slope, and the unit is degree percentage on topo. And this clinometer compass, it is fixed to a rectangular plate. The plate may be made of cast iron or plastic, and the 180 degree line, that is the north-south line, is made parallel to the length of the rectangle, longer side of the rectangular plate, and is marked 0 to 360 degree, marked in the anti-clockwise direction in clinometer compass. Okay, whereas in the Brunton compass, this is Brunton pocket compass. It is highly precise and it measures the strike and dip of the rock layers. So here it is strike and dip. Okay, and Brunton compass, it has folding open sides. You can see in the figure. This is very similar to the prismatic compass. Okay, there were two one sight vane and object vane hinged to ends. So you have seen prismatic compass in survey. So similar to that, here also we have two sights. There is a mirror is there. Then you have a rectangle shaped spirit level is there. So it can be used in hand. Okay, or you can place it on a staff or on a road, on top of a road you can place it, and and you can read the magnetic bearing of the line. So mainly Brunton compass is for the measuring the strike and dip. So with that we complete this particular topic. Okay, thank you.